Hello, everyone. My name is Fabiana Morales. I'm from Venezuela, but now I'm representing the Argentina National Atomic Energy Commission. And I will talk to you about magnetocaloric effect of lanthanum strontium cobaltite nanoparticles. Let's start from the introduction. What is magnetocaloric effect? Well, it's a heating or cooling of a magnetic material when the applied magnetic field change. This could be defined by two ways. The first way is when the adiabatic temperature change, and we can measure this directly with a thermometer. And the second way is an isothermal change in a magnetic entropy. And we can measure this indirectly. Why? Because we have to measure two curves of the magnetization versus magnetic field at near temperature. After that, using the Maxwell relation, we can find the magnetic entropy change. Both measures ways are related through the heat capacity. And with a large entropy change, we will have a large entropy, a large temperature change, sorry. Well, which synthesis methods we use? We will use the wet method that implies stirring distillate water with nitrate solution at 1 molar of concentration. This stirring is under an acid pH for avoided precipitation. Well, after that, the solution was added into 800 and 200 nanometers porous polymeric membranes. And after that, we apply a thermic treatment at 800 degrees and 1000 degrees. From this synthesis, we obtained 4 samples designed as C2T1, CH-T1, CH-T2, C2T2. What does this mean? C is for cobalt, 2, and H is for the size of the membrane, and T1 and T2 is for the thermic treatment. What characterization we will study? X-ray diffraction, scanning microscopy, vibrating sample magnetometer, and from this one, we will study the magnetic characteristic and the indirect magnetocaloric effect. Well, which structure and shape it has? From X-ray diffraction, we found that the sample shows an orthorhombic perovskite structure, and also we obtained the crystal size for C2 for all the samples, and we found that T1 samples have a smaller size than T2 samples. And from the scanning microscopy, we found that the 200 nanometers millipore samples, I mean C2 samples, have the nanowire shapes and the nanowires, and the CH samples have nanotube shapes. Well, using the vibrating sample manometer, we obtain the MH curve, that means magnetization versus magnetic field, yeah. From this curve, we have the coercive field and saturation magnetization for the 4 samples. And here we have a summary of this. We can see that the T1 samples have larger values for coercive fields and smaller values for saturation magnetization. And on the other hand, with the T2 samples, this and this, we have lower coercive field and large saturation magnetization. What we want, or what we shared? We shared a lower coercive field and large saturation magnetization. Why? Because this will make easy a magnetization and the magnetization cycles And this means that we will have a large magnetic entropies values. Okay. Here we have the magnetization versus temperature curves and blockade temperature for each sample, and the inset, the inverse of susceptibility versus temperature. We have this for all samples, and here we can see the Curie temperature are higher for T2 samples than for T1 samples. Well, using the magnetization versus magnetic field curves and the Maxwell relation, we can find the magnetic entropy change versus temperature. Here we can see all curve for 10,000 Ersted, 20,000 Ersted, and 30,000 Ersted. For T1 samples, we can see a wide curve down for T2 samples, and also we can see large values for T2 samples than T1 samples. From this curve, we can study the refrigerant capacity, that it is the capacity of heat transferred between the cool and hot spot in an ideal thermodynamic cycle. How we can obtain this from the last curves? Using the magnetic entropy mass change and the width of the peak. Here we can see the refrigerant capacity for all samples, and again, for T2 samples, we have higher values than for the T1 samples. And in the figure 9, we can see a comparison between literatures and our samples. Our samples are here, and the rest are from the literature. And we can see that our samples are in the same range, almost, that the reported in the literature. Well, what we learn from this? With a large particle size, we will increase the saturation magnetization and decrease coercive fields that make easy magnetization and desmagnetization cycles. And this imply a bigger entropy magnetic values. And also we have a transition temperature nearest room temperature. Well, what about the step? We want to study the change of magnetic entropy with an iron addition in the structure here. And we want to study a variation of the added iron. Well, this is all. Thank you so much. And I wait for your questions.
Thank you very much, Fabiana, for a wonderful talk. I have a little question regarding the sizes you got in your samples. What happens in between? Because you have, I think it was 200 and 800 nanometers. So have you tried intermediate sizes or?
Now I don't have any other sample from these samples. I only have these 4 samples because these measurements are from the pandemic, and we couldn't make more samples from this. But we want to make more samples and build I forgot.
Other sizes.
Yeah, we want to study from the, for example, if we have a cobalt, we want to study the medium sizes and with the add of iron.
Great.
True.
Great, that answers my question. There's another question also related to size from Sonka. It says, Is it simply the size of the samples that leads to the higher saturation and lower coercive field of the T2 samples, or does the structure matter?
Could you repeat the
Yes, yes.
It's simply the size of the samples that leads to the higher saturation and lower coercive. This is the question or another one?
Yes, it's
okay.
The question.
Okay, it is simple the size of the samples that lead to higher saturation and lower coercive, right? T2 samples, or does the structure matter? I think it's only the sizes, because when we study the X-ray diffractometers, we see the samples that have a higher treatment of temperature, has I don't know how increase the crystal size, and also we can see a better magnetic behavior. And with the low temperature treatment, we see the results I already told you. And I think it's only about it, because I didn't see any other, like ¿cómo se dice impureza? Sorry. Another
extra
compound
phases.
Another phase in the structure.
But what about grain size or crystalline size? Maybe that can have a bit of influence in the magnetic behavior.
Yeah, this is the final objective of this work, that shows the crystal size have a big influence in the magnetic behavior, because if we see the T2 samples has better behavior than T1 samples. We have here a higher magnetization saturation, and we also have a lower coercive field.
Okay, so these sizes were extracted from a Scher equation, maybe? The particle sizes? That's directly
for the Wilson-Holtz method. And we made first of all, we made a Rydberg. And after that, we used these results for make a Wilson-Holtz. But I decided to only show the magnetic characterization here.
No, it's okay. It's perfect. And we are right on time, so it's a great choice. So thank you again, Fabiana. If somebody else has a question, can find you maybe in Gather Town later.
Yep, thank you.